Welcome to this lecture on single phase flip flop design and operation. This is a part of module 3 on sequential circuits in near threshold voltage. So, we will first discuss the importance of single phase flip flops, and then we will discuss a very popular single phase flip flop, true single phase clocked register, and then we will discuss a popular highly cited single phase flip flop more appropriate for near threshold voltage operation. So, when you have two clock phases, you need to either mostly locally generate the complement of clock, and that results in a larger power consumption because of complementary clock signal. There is also an offset between clock and clock bar. So, if this is the clock signal, and there is this clock complement signal, there can be an offset, because in generation of the clock bar you might have some inverter stages which could cause a So, what would this do? Say in a transmission gate, when you have, which is a part of the, suppose if you are looking at static latch, you have a transmission gate in it, and you would connect the N MOSFET to clock and P MOSFET to clock bar. You would see that if there is a change in signal, the signal D, suppose it changes after the clock edge, suppose it changes here. Since it is after the clock edge, the signal is not supposed to pass through the latch, but you would observe that because clock B is still has not and there is a delay, there is an offset between clock and clock B. So, it would result in a chance that a part of D, that is if D is rising from 0 to VDD, you may find that it would partially rise, Q would partially rise, and that would give rise to glitches, or it may even give rise to a wrong latching of the signal. So, these kind of violations can occur because of the offset between clock and clock bar if you do not have single phase clock. And also if you have a single phase clock, therefore, the setup and hold, due to these reasons, the setup and hold time violations would be more avoided. Setup and hold time both would become smaller. So, for example, here till the clock bar switches completely, safely you would say that the hold time is till the clock bar switches completely. So, if there is a single phase, you would just take the clock transition time into account, you would not take this offset into account. So, that will reduce the hold time. So, the most popular single phase clock is true single phase clocked register. So, how does this function? Suppose, so let us have a ideal clock. Let us understand through an ideal clock. If the data D is 0 initially, when the clock is 0, suppose the data is 0 and it changes from 0 to VDD when the clock is 0. Then what would happen to the value of node X? Since this P MOSFET is on when clock is 0 and this P MOSFET M2 is on when clock is 0, M3 is on since data D is 0 initially, but then when data D turns 1, M3 is off. So, it is only M2 which is on now, M3 is off. So, there is no connection to VDD, but because M3 was on initially, when data was 0 and clock was also 0, x is charged to VDD, x is initially charged to VDD. But then once the data turns to VDD, M3 is off, M1 is on. Now M1 is on, so therefore x would get discharged. So you would find that x discharges from VDD to 0. Okay. Okay. And what happens to y? When clock is 0, M6 is on. Therefore, y would have been pre-charged to VDD. Because clock is 0, M4 is off. So, therefore, whatever be the value of x, either VDD or 0, y would be pre-charged to VDD. So, x is now discharged, and therefore, when clock turns high, y would not change its value, y would remain at VDD. This is an ideal timing diagram that I am drawing. Y would remain at VDD. What about the value of Q bar? Now, since Y is VDD, M9 is off, M7 is on, and when clock turns high, M8 is also on. So, Q bar would turn to 0 as it is required. D is 1, so Q bar would turn to 0. Q bar would turn to 0 from whatever value it has. Suppose it was at 0, even then it would go to 0. From whatever value it has, it would turn to 0. Okay. Suppose now clock turns to 0 again. When clock turns to 0, this is off, this is pre-charged to Y. So, M9 is off, M8 is off, Q bar would remain at its previous state, whatever be its state. If it is 0, it would remain at 0, because both pull up and pull down are off and it is a dynamic circuit. Here it is held. This is the hold state. Okay, this is the functioning. Now, we can see the other case where D turns from VDD to 0. If D turns from VDD to 0, here VDD to 0, that is, we are seeing this case, then when the clock, so since it has turned to 0, M3 would be on, M2 is already on because clock is 0 and clock is in the hold state 0. So, x would turn high, and when clock and y would be pre-charged to VDD, but when clock turns to 1, state 1, M6 is off, M4 is on, y would get discharged, and since y would get discharged, M9 would turn on and it would charge to VDD, and M7 is off because y is going to 0, M7 is off. So, Q bar would charge to VDD. So, that is the functioning of this. This would y would discharge here after the clock turns high, and once y has discharged, Q bar would turn high. So, this is the functioning, and when clock equal to 0, y would be pre-charged to VDD, therefore, Q bar would be in hold state. So, this is the functioning of the TSPC flip flop, but there are some issues with the TSPC flip flop. So, one of the major issues is the glitches. So, here an example has been shown. So, when the clock turns high and the input data is 0, so therefore, x turns high. When clock is 0, x turns high and y is precharged to VDD. So, that would put off M9, but y would now turn from VDD to 0. But initially y is at VDD, and when clock turns high, M6 is put off and y would discharge through M5 and M4 in this case. D is 1. So, in that case this glitching would not happen. Suppose D is 0, x is turning from 0 to 1, D turns from 1 to 0, x turns from 0 to 1, logic state, y after the clock edge it turns from 1 to 0 after the clock is equal to 1. So, in the mean with a delay, okay, there is a delay involved. So, in the meantime M7 is on. In the meantime, during the transition from 1 to 0 of y, M7 is on and M9 is off. So, in the meantime clock is on. If clock transition time is small, clock is on. So, M8 is on, M7 is on initially. So, Q bar would get discharged as it is happening, and it would take a while for M7 to turn off and M9 to turn on. Once that happens, Q bar is again restored to the required value. But there is a glitch. Glitches cause unnecessary power consumption because that is discharging happening, unnecessary discharging, partial discharging, and glitches also can cause signal transition problems, which can, if the glitch depth is larger than the inversion threshold of this inverter, you would also see change in state of Q, a transient change in state of Q, which can pass on to the logic circuit ahead. So, these kind of issues can arise because of these glitches. So, this can be improved by modifying the circuit, by increasing the size of M5 and M4. You can reduce this delay, and also reducing the size of M8 and M7, you can reduce this delay, but that would, increasing the size of M5 and M4 would increase the power consumption of the circuit, and reducing the size of M8 and M7 would result in a larger discharge delay here of Q bar. Okay, so, whenever D is 1, you will take longer time to discharge. So, that is therefore, all these kind of design solutions have a cost associated with them. So, and also the node Q is a dynamic node, node X is a dynamic node. Okay. So, these are dynamic nodes, and dynamic nodes can have, node Y is also a dynamic node when clock is turning high. Clock is turning high, X is 0, that is when D is 1, X is 0, clock turns high, M6 is also 0 off, M5 is off, node Y is dynamic. So, dynamic nodes have a problem that any noise, or suppose there is a coupling capacitance from here till some other circuit, and you find a transition here, or and you find a low going transition here. Clock is 0, X is 0, Y is supposed to be at VDD, but Y would see a from VDD a fall because of this coupling capacitance. That can partially turn on M9, which is supposed to be off. So, these kind of issues because of coupling capacitances can also be there, and a little change in the voltage here can cause an issue, because you would find that the change in current can be exponential in near threshold regime with a little change in gate voltage. So, these kind of issues are there with all dynamic circuits, and therefore, these kind of dynamic circuits are not very easy to use in near threshold regime. So, we will discuss now a flip flop which is specially proposed for near threshold voltage operation, but has this single phase clocking feature. This flip flop has 24 transistors and it has a single phase feature, and it is more suitable for a near threshold voltage operation, because always every node is connected to either VDD or to ground. Therefore, there is no dynamic node, and because of this the noise or coupling noise disturbing the circuit functionality would not happen. Also, this circuit does not have the problem of glitches. So, power consumption and erroneous signal propagation, these issues are also not there. So, this is more amenable to near threshold voltage operation. So, how does it function? When data D is 0 and clock is 0, this transistor is on, this is also on because D is 0, and this is this net 1, this we call net 1, this is net 2. So, net 1 is on, net 1 is at VDD, not on, and so net 1 is at VDD or logic state 1. So, that would cause net 1B to be at logic state 0. And what about net 2? Because of this clock, net 2 is precharged to VDD. When clock is 0, because of this transistor, net 2 is precharged to VDD. That turns on these transistors, but that does not affect this feedback loop here, and this is in a hold state, because Qn is not connected to either pull up or pull down through this path, and therefore, it is a back to back connected inverting stages. So, this is an inverting stage. When clock is 0, this is on, and because net 1 is on in this case, this is also on, therefore, this is also an inverting stage. So, it is now in a hold state, Qn is in a hold state. So, what happens when clock turns high? D is still 0. So, what would happen? Now, this transistor is off, this has turned off, net 1 is at VDD, net 2 is precharged to VDD initially, but now since this transistor is on, because net 1 is on, so this transistor is on, this transistor is also now turned on, because clock is now VDD, clock is at 1, logic state 1. So, net 2 is pulled to 0. Since net 2 is pulled to 0, in this cross coupled stage, you find the cross coupled P MOSFETs, you find that this P MOSFET is on, turned on, and net 1 is again connected to VDD. So, net 1 is not dynamically at VDD, it is statically connected to VDD. So, but net 2 has turned to 0 and it is again connected to ground, static connection. So, it is a static scenario, and since net 2 turns to 0, this transistor turns on and this is on, but the pull down path is off, because net 1B is off and also this is turning from VDD to 0. Therefore, this is also turned off. So, Qn is charged high as is required, D is 0, Qn is high. Hold state we have discussed already. Now, what about the scenario when D is 1? So, now let us discuss the scenario when D is equal to 1. So, when D is 1, this transistor is off, this is on, and clock is 0, but still pull up is off, pull up path is off. So, net 1 is now pulled to 0 because these two transistors are on. Net 1 is pulled to 0, but clock is 0, therefore, net 2 is precharged to 1, net 2 is precharged to 1, and also this transistor is on, that also charges net 2 to VDD. Okay, net 2 is precharged to 1 and net 1B is also charged to VDD, because net 1 is 0, net 1B is at VDD. So, these two transistors are on, but pull down path is off because clock is 0, and since net 2 is at VDD, this transistor is off. Now, when clock turns high, this transistor is on, and since net 1B is at VDD, this transistor is also on. Therefore, net 0 is connected to ground again statically, net 0 is connected to ground. Net 2 is connected to VDD through this transistor which is on. Of the cross coupled PMOS transistors, this transistor is on, net 2 is connected to VDD. And now, since clock is on, clock is VDD, therefore, the pull down path here is on, and therefore, Qn is discharged to 0. Okay. So, therefore, you would find that D is 1 and Qn is discharged to 0, and all the nodes are connected to either 0 or VDD. So, there is no contention because of noise, etc. That is the main advantage of this, and therefore, it is more amenable to near threshold voltage operation. What is the setup time of this flip flop due to? So, what should happen before the clock turns high? So, once the clock turns high, when D is 0, once the clock turns high, this should Qn should get charged through this transistor. So, we should find that this transistor is on once the clock turns high, because once the clock turns high, there is no path, this path is connected to 0 through this, but that would happen only if this transistor is on. If this transistor is on, this would be pulled down to 0 and this would turn this Qn high, this transistor, is not it? But net 2 should be pulled down to 0. Net 2 would be pulled down to 0 if net 1 is at VDD or net 1 is charged high. So, what it means is that net 1 should be sufficiently charged high before clock turns to VDD. Before clock turns, because after clock turns to VDD, net 1 can turn to VDD only if net 2 is discharged through this. Net 2 is discharged and then this transistor would connect net 1 to VDD, but that would happen only if net 2 is discharged. Net 2 can discharge only if this transistor is sufficiently on. Remember, this is near threshold voltage operation. So, the VGS of this transistor while discharging is anyway smaller, because this node would be at an intermediate voltage and this would be having a VGS which is smaller than VDD, even when net 1 is at VDD. Suppose net 1 is partially charged. So, this data D turns to 0 just before the clock turns high, and the offset between data D and clock turning high is not sufficient, suppose. So, in that case, if this is the clock turning high and data D turns to 0 very close to the clock edge, then net 1 would not sufficiently turn high. Suppose it turns to VDD by 3, and in the meantime you find that one has not sufficiently turned high. Therefore, in that case, this transistor after clock turns high, this would not be sufficiently on, and therefore, the discharge of net 2 would be very slow. That would result in this transistor not turning on, and therefore, net 1 would remain at a low voltage, at a voltage which is lower than VDD. It would nevertheless charge a little, but very slowly. Net 2 would also discharge, but it would discharge very slowly. And therefore, you would find that net 1 would also charge up very slowly, like this. So, it may turn that net 2 is discharging very slow, and therefore, this transistor does not turn on and Qn does not switch to VDD. So, this can result in a setup time violation, and therefore, you should have net 1 discharged to VDD before clock turns high. So, setup time therefore is that the delay of charging net 1 from 0 to VDD, the pull up delay, setup time or pull up transition time of net 1 which is charging through M1, M2. Now, let us see what is the setup time when D is equal to 1, that is when D is turning from 0 to VDD. So, what happens when clock turns high? When clock turns high, net 2 is at VDD net 1 is 0 and net 1B is at VDD. So, this is QN discharges through this to 0. So, for that net 2 should be at VDD, which happens due to the precharge anyway, and net 1B should be at VDD, net 1 should be discharged. So, it means the critical thing is that net 1 should be sufficiently discharged. In that case, this functionality will happen. Otherwise, if net 1 is not sufficiently discharged, net 1B would not be sufficiently charged high, and therefore, you would not connect net 1 to ground through this transistor, and also this transistor would not be sufficiently on, and therefore, QN would not discharge within time, may not discharge within time. So, therefore, the setup time in this case is equal to the pull down transition time of net 1 through M3 M4. Now, let us discuss hold time. Let us discuss the hold time of this circuit. So, after the clock turns high, suppose D turns from 0 to VDD. Now, net 1 is at VDD, D turns from 0 to VDD, and this transistor M2 is off anyway because clock has turned high. D turns from 0 to VDD, and therefore, net 1 can be, but this transistor is off. So, net 1 is not affected. So, from when D turns from 0 to VDD, 0 to 1, net 1 is not affected, though this transistor is on, but this is off because this has turned from 1 to 0. But in the meantime, before this has turned from 1 to 0, if D turns from 0 to VDD, then you would find that net 1 can be partially discharged and net 2 can also be, so both net 1 and net 2 can be partially on and therefore disturb QN. So, the whole time would be the discharge time of net 2. Discharge transition time of net 2 through path as shown. Likewise, let us discuss the hold time when the input turns from 1 to 0. Input is 1, but after the clock transition it may turn to 0. Let us discuss this scenario. Ideally, if D turns to 0 after the clock is VDD, anyway pull up path is off, even when D turns to 0 this is on, but this transistor is off, and therefore, net 1 which is 0 would remain at 0 and it is connected through this path. So, therefore, it is remaining at 0. But suppose before net 1 discharges to 0 and net 2 remains at VDD. So, net 1 has turned to 0 when clock turns high, and before clock turns high, because D was 0, net 1 was already at 0, and in this case net 2 was already at 1 because it was precharged through this. So, both net 1 and net 2 are having the required states before the clock turns high. So, in this case the hold time should be 0. The authors of the paper have also compared the hold time for 0 to 1 case, input from turning from 0 to 1 after the clock transition, with the static flip flop, static transmission gate based flip flop, transmission gate flip flop. So, here the hold time is because of the difference in the clock and clock bar. So, as you can see, the hold time can be because of the transition of signal from here till here. So, suppose clock and clock bar have an offset, and therefore, there is a change in D after the clock edge, but it can pass through the partially on. So, one of the transistors would be still on. So, it would pass through the partially on transistors, and there can be a glitch at the output. But this is passing through several stages and it is prone to variability. Whereas, in this case it is limited by the delay of this path as we had discussed, and only these two transistors. So, there it is less prone to variations, that is what they have found. The hold time is less prone to variations. Here, as you can see, the average hold time is quite small. That is because the hold time from the D turning from 1 to 0 transition is 0 as we have discussed, and it is only the hold time from 0 to 1 case which is important for this S square CFF. And as you can see, as you reduce the supply voltage, the hold time increases by several factors. It increases from about 0.2 units to about 0.6 units. So, 0.2 to 0.6 units, about 3 times increase in the hold time from VDD 0.8 to 0.3 volts. So, as can be seen, this S square CFF, this flip flop operates till 0.4 volts and it avoids glitches, and its variation of clock to Q delay, setup time, hold time is lesser. The hold time variation is also quite small as we had seen, and it is all the nodes are connected statically to VDD or ground, and it is single phase, that is an advantage. And here you can see that the measured clock to Q delay, for just for a comparison, at nominal voltage is around 30 picoseconds, and at 0.4 volts it is around 400 picoseconds. So, that is quite a significant increase in the clock to Q delay, but that is a feature of all the near threshold voltage circuits. So, these results are for a 45 nanometer PDK. So, in this lecture we have discussed single phase clocked flip flops. We first discussed the traditional TSPC flip flop and and also limitations in near threshold voltage operation for TSPC flip flop. We then discussed S square C flip flop, and that all the nodes in the S square C flip flop are always connected to either VDD or 0. So, it is contention free and also glitch free. We discussed its setup time, hold time and clock to Q delay and minimum voltage at which it has been shown to be operating. Thank you.